In this video, we are going to talk more about the sampling distribution of the sample mean. So this is section 7.3. All right, so we already mentioned this in 7.2, but we talked about the sampling distribution of the sample mean for normally distributed variables. And the thing that we didn't mention there, and that's kind of new for this section, is that is the exact distribution of the sample mean. So suppose that we have a variable x and it's normally distributed, okay? And it has a population mean of mu and standard deviation sigma. All right. So last time we talked about the sampling distribution of the sample mean. We didn't really mention it, but we said that for if you take samples of size n, then the variable bar x, right, the sample mean, is also normally distributed. So that's the part that we didn't really talk about last time. So if you have a normally distributed variable, you take samples of size n and look at the sample mean. We talked about last time that that was a random variable and that it had whatever its mean was and its standard deviation, right? But what we didn't mention last time was that it was normally distributed also. So if you start with a normally distributed variable, then the sample mean bar x bar is also normally distributed. And last time we mentioned exactly what its mean was, right? Its mean is the same as the population mean. And the standard deviation for x bar is sigma divided by square root n. The population standard deviation divided by the square root of the sample size. All right, and so in addition, right, if the variable that you start with is normally distributed, then so is this bar, x bar, the sample mean. Okay. All right. Now, so that describes the situation when the variable that you start with is normally distributed. But how about if it is not normally distributed? Okay, well, if it's not normally distributed, right, then the situation basically depends on the sample size, and that kind of boils down to something called the central limit theorem. So what the central limit theorem says is that for a relatively large sample size, right, the variable x bar is approximately normally distributed, regardless of the distribution of the variable under consideration. Okay? So it's nice if you have a normally distributed variable. The previous slide says that the distribution of x bar is normal, right? This one, right, the central limit theorem says that as long as you keep the sample size large, okay, then the distribution of x bar will be approximately normally distributed. And the approximation is better and better with increased sample size. So for our purposes, we are going to go with a sample size of 30 or more. So even if you start with a distribution that might not be normal, say x comes from here, and so this one is right skewed, right? So this one would be not normal, right? If we took samples of size, say n equals 100, right? And that's bigger than our cutoff of 30 here, we would know that this, the distribution of the sample mean, right, would be approximately normal, okay? And so therefore we can use some of the techniques that we've been using so far, okay? All right, so now the explanation of why that's true is kind of difficult. So I'm not going to explain it, but I did find a simulation, and so it's better if we look at the simulation here. So the simulation is in this link right here, so you can go to that link and try it out for yourself if you like to. Okay, All right, so what we have here is a histogram, right, for some population. Okay, here over here you can see the values of the population. So the population has the possible values 0, 1, 2, 3, and 4. Okay. All right, and then what we are going to do, and you can change these distributions right here. Okay. So we're going to be sampling from this box distribution, right? And this is the histogram for the box distribution. You can see in the histogram all of these are equally as likely. Okay. And then what I'm going to do is take a sample from the box distribution. Here the sample size is 5. Okay. So I took a sample of size 5, and here I calculated oops, that was the sample sum. I didn't want to do that, so let me start over. I was going to say that's weird that it came out to be 12. So I want to calculate the sample mean. Okay. So again, this is the box distribution. Okay. And so here's the histogram for the population. I'm going to take a sample of size 5. All right, so I took a sample of size 5, and the mean came out to be 2. Okay. And then I'm going to take another sample. All right, it came out to be 2. All right, that's a third sample, and you can see it came out to be something between 2 and 2.5, the sample mean. All right, and so I'm just going to keep doing that. So the green histogram, right, is the histogram for the sample means that I'm taking. So far I've taken 20 samples of size 5 from this population, and the green histogram is a histogram of those sample means. I'm going to turn the blue population histogram off so we can only focus on this histogram, which is the histogram of the sample means. Okay, so I can keep taking those. All right, and what the central limit theorem says is that even though the population histogram, right, this variable is not normally distributed. I can tell because the histogram looks like a rectangle, right? Okay, and we know that the normal distribution does not look like a rectangle. It looks like a bell-shaped curve, right? All right, and so we are sampling from this population that's not normally distributed, right? So if we keep doing this enough, taking these samples, all right, and I am going to skip ahead and now take 100 samples at a time. All right, and you can see the more samples we take, all right, so we're up over 5,000 samples take. What is the histogram starting to look like, right? It's starting to look like a bell-shaped curve like that, okay? Okay, and so that illustrates that. Now, let's take a look at samples of a fairly large size, let's say 50. And we're going to take 1,000 samples at a time now. All right, so even though the population, right, that we're sampling from is not normal, right, because of the large sample size, we can see after taking 10,000 samples of size 50 and look at its histogram, right, that looks approximately like a normal distribution, right? You can see it looks just about like a bell-shaped curve there. If I take that off, it will zoom in a little bit, and you can see it's not exact, right, but it's pretty close. Okay. All right, so that's sort of a simulation that shows that. You can try and reset this oops, I did sample sum again. Sorry, I should have done sample mean. But here's another distribution, the uniform distribution. And start taking samples from that uniform distribution. Now I'm taking 100 at a time of size 50. Turn the population histogram off so we can focus on the histogram of the sample means that we've taken. All right, and you can see that that is looking pretty normal. And then of course, if we start off with a normal, right, distribution itself and take samples from it, right, we can see that the distribution of the sample means looks normal again. So that's not a proof, right, of the central limit theorem, but it is sort of an illustration that says, hey, regardless of where that the variable that you start with, its distribution, right, as long as we keep the sample size large, 30 or bigger, right, then the variable is going to, or the distribution of the sample means is going to be approximately normal. So that's why we kept getting those bell-shaped curves for those green graphs there. Okay. Okay. All right. And so next, this is sort of a summary of what we've done. So suppose you have a variable x and it has a population mean mu, standard deviation sigma. Then for samples of size n, the mean of x bar is the population mean. The standard deviation of x bar is the population standard deviation divided by the square root of n. If x is normally distributed to start with, then so is x bar, regardless of the sample size. And then if x is not normally distributed, then x bar is approximately, the distribution of x bar is approximately normally distributed, or an approximate normal distribution, regardless of the distribution of x, as long as the sample size is large, and that's 30 or more on that. Okay. All right. And so in the next videos, we will work through some of these book problems. In the book problems, we talk about calculating probabilities related to the sample means.